the predictive capability of these models is. Modern geometric models, as they are used in the minerals industry or in water flow simulations or in oil and gas field exploration and production, are usually built upon a database. There are lots of informations of measurements in cores, in seismic, and maybe field. And these are all coupled in a database. And the result of this database is this geometric model. And the database is automatically updated when you get new data. It is quite normal that you have your geometric model, and then you drill a little bit further in your mind, you get some more information, you put it in, and then the model is a little bit adapted. And so the model will get more and more accurate with time. But at the same time, the importance of the model is decreasing. Of course, what you want, if you have a mine or if you have an oil field or some kind of a geothermal reservoir, is you want to have a model which predicts everything right at the beginning. Then that is the $1 million challenge. But in the beginning, when you don't have a lot of data, your models are not so accurate. After the end of your oil field, all the oil that has been produced, your model is perfect. But it's not very useful anymore because you cannot make money with it. Okay? So the challenge is to make your models as good and as accurate as possible early on when you don't have a lot of data. The next class of models are kinematic models. Now, what is kinematic? Kinematic is motion, in German, the Kino. They show not just the shape, but the change of shape. So, for example, you have a layer, and the layer is folded. A kinematic model could be a movie that shows this. Okay? And then you could play it back and unfold the cookie. That is kinematics. And there are very elaborate three-dimensional computers programs nowadays which allow you to unfold, to undeform parts of sedimentary basins or mountain belts. And they are very useful. But the thing is, kinematic models are not mechanically constrained. What I mean with mechanically constrained is that you can draw with these kinematic models all kinds of things which are physically not possible. A good example is one of these cartoon books like Asterix. You can draw all kinds of things which are really not physically possible. If Asterix hits one of the Roman soldiers, it is not possible physically that that person would fly into the air 5 meters. Okay? So kinematic models can be very useful, but one also has to be very careful with kinematic models because they can be really wrong. They are not constrained by mechanics. Dynamic models would be models where I just don't describe the change in shape, but at every point in this cookie, I tell you the forces, and I tell you the properties. Okay? Dynamic models are much, much more complete. Therefore, they are much, much more difficult to make, dynamic models. They are not as detailed as one would like. They are very, very strongly in development at the moment. They include the forces, the material properties. Some of them are physical models, and some of them are numerical models. And now I will give you examples of each of these, the geometrical, the kinematic, and the dynamic models. Okay, this is a very simple geometric model. There is no kinematics here. It is just a geometric model. It is from a beautiful postcard from Crete, layered rock which is folded. And then it is broken into folds, and the different colors, they show you different layers. which have been carefully marked by different colors. And then the orange one is again a different layer. And then there is the green one, and so forth and so forth. So this is a geometric model. And to create such a model, there is a continuous process of interpretation. For example, here I have this orange layer, which I called orange. It takes you quite a long time to make sure that the layer here is actually the same as there. You don't see that it is continuous. So you start counting layers, you start comparing the shape, and then you say, okay, I convinced myself this is my interpretation, it is the same. And interpretation is an essential part of what a structural geologist or tectonician does. What is very important, and people make many mistakes in the exams, it's important to state the basis of your interpretation. You don't just say, hey, this layer is the same. You say why. What did you assume to come to that conclusion? That is the basis of the interpretation. Geometric models. This one is two-dimensional and very simple. This one here is three-dimensional, and it's very complicated. What you see here is the result of maybe $50 or $100 million of data acquisition, geophysical data acquisition. It is a small part of the subsurface of the North Sea. Down here, the wells which are going into the oil fields are shown by these very thin lines here. And the different surfaces are the tops of different geological units. For example, this one is the unit which is the reservoir, and it is colored according to the amount of oil which is there in different places. So the production geologist can say, the red color is a lot of oil, so I'm going to drill into that particular place to extract the oil. This one here is the top of salt. And maybe you have all heard about salt domes. Salt can form very complicated structures in the subsurface. And here is one of these. These are very complicated geometrical models. And they can be amazingly accurate. You know, the accuracy of many of these layers is up to a few meters at several kilometers depth. And then this kind of accuracy is passed on to the drillers, who have to make sure that their drill hole hits exactly that spot. So these are the geometric models. Now let's go and look at kinematic models. How do we extract motion from rocks? And there are different ways. You can look at small-scale structures, for example, little garnets in crystalline rocks. This would just be a few centimeters, or pieces of feldspar crystal. And they tell you quite intuitively that there has been a certain amount of motion. Okay? And if you look at structures like this, if you learn to identify them in the field, then you can extract that in this particular place there was motion in that direction. Okay? Slickenside, Harnische, okay, are similar indicators of the motion, like this. Much larger and much more complicated models are based on an interpretation of a structure in the subsurface. This is, for example, a geometric model of the subsurface of Germany. All the different colors show you different layers. So this is the Tertiary, this is the Cretaceous, this is the Permian, and blue is salt. So this is a salt dome. And with kinematic software nowadays, you can remove these layers one by one. Okay, so what you do is, this is where you start, and you remove the Tertiary, and you move all the layers and the faults back into their position that you think they were in. Then once you're satisfied, you remove the Upper Cretaceous, and you do the same, then you arrive at a time where there was a lot of salt at the end of this extant time. And now, of course, you can play it in this direction and really reconstruct the kinematics. But the important thing is, these models are very complicated. They show you very beautiful movements. But the fact that they show you these movements doesn't mean that the movements must be true. Okay? Because these models are not mechanically, dynamically constrained. So now we have seen the geometric models, we have seen the kinematic models, and the final class of models that we have in structural geology is dynamic models. Dynamic models, that's the kind of models where you have the forces and the displacements and the material properties all in one model. So dynamic models are very complete. They are very physical. But therefore, they are also very difficult to really produce. Remember, we can't go into the earth. We cannot measure the properties of the rocks over millions of years. So many of the numbers, many of the parameters that go in these dynamic models are not so well understood. But dynamic models can be extremely interesting. And I'm going to show you one model here, made by Hein, one of our PhD students, of a simple graben structure. You, of course, all know what a graben is. It's extending piece of crust of the mid-oceanic ridge. So what you should see is that there are here two faults, this mid-oceanic ridge graben, and above it is a lot of basalt, which is rather hard and strong rock. And now we are going to deform this. So these basement faults are moving down, the crust is extending, and the basalts develop a very complicated series of fractures. The rock breaks, the fragments are moving along each other, there are pieces falling down into these grabens. And this is a so-called scaled physical model. Now, what does that mean? It is a physical model because we want to reproduce something which is much bigger, so somewhere deep in the earth, using physical materials. We have the same kind of boundary conditions, that is, we are pulling, and there is this graben in the middle, which is going down. And then what we would like to try to achieve, the model which is deforming and deforming, same structures that we have in nature. Then it is a good model. And to have a model work in this way, we have to scale it. A model that is scaled has reduced or increased by the same amount that is required to make the model scaled. I would like to just give you an example now, and further details of scaling will come in lectures in your studies. Imagine that you are asked to build a new dome in Aachen, which is 500 meters high, enormous Aachen dome. And you are asked to make that out of the Maastricht limestone. Okay, you say, that's very nice. Give me the drawing, and they give you the drawing of this beautiful new Aachener dome. I'm going to make a small model. So the 500 meter I reduce to 1.5 meter. Therefore, I take the Maastricht limestone, I make very small blocks out of it, I pile them on top of each other, I make my model, and look, it stands up. It's beautiful, maybe I shake it even a little bit, it stands up. And therefore you conclude the dome which I'm going to build for a lot of money, 500 meters high, is going to be stable. Okay? Now this argumentation is wrong. And most of you probably know why it is wrong. Because if you reduce the size